Okay, so we're still doing a bunch of Atwood machine problems. Today's problem, I'm going to look at the half Atwood machine on an incline with friction. Yes, things are starting to get complicated. That's what makes it fun and awesome. So let's just do a quick summary here of the kinds of problems we've done. I have a little sheet here I made just for you. So I started off with the Atwood machine, which is just two masses over a pulley, found the acceleration. The half Atwood machine is a mass on a plane with no friction and on one mass hanging over the edge, found the acceleration. Here's the inclined half Atwood machine, which I don't know what the name of it is. That's what I call it. I did that one. I found the acceleration. Then I did the velocity after it falls a bit, and then I did the half Atwood with friction. And then I did another problem to decide what was the minimum coefficient of friction. Okay, so this is actually no friction solution. I put it down here because it'll be useful to compare. Okay, that if there's no friction, that's the acceleration of block 1, assuming that it accelerates down. Okay, and again, this one we're actually going to get, it could be accelerating down or up. But let's just say it's accelerating this way. And that one's going that way. So this brings my first main point about these masses. If this mass moves down 1 centimeter, that one has to move up the angle 1 centimeter in the same amount of time. So they have the same velocities with different directions, and therefore they have to have the same acceleration. So the magnitude of the acceleration for 1 has to be equal to the magnitude of the acceleration for 2. That's just, if the rope doesn't stretch, that has to be true. The other thing is, if the rope is massless, then the tension over here on mass 2 has to be the magnitude over here. So I can write T1 magnitude equals T2 magnitude. They're different directions, okay, but those two are different. And this is true for my inclined planes with frictionless ropes and frictionless pulleys and massless pulleys. Once the pulleys have masses, this is no longer true, but we'll do that in another problem. Okay, so I'm going to start off. Oh, and the other thing I need to know is let's just say it's sliding. Okay, I'm going to not even worry about static friction. So I'm going to use the frictional force magnitude is equal to the coefficient of kinetic friction times the normal force. Okay, let's start with this mass right here because it's easier. So if I draw a force diagram for that mass, I have this. I have M1G, and then I have the tension. And I can say F net Y is going to be equal to T minus M1G equals M1 negative M1A. I'm assuming it's accelerating down. And so here's the place where you have to be careful, right? You cannot say the tension is equal to the weight, even though I did that in the past. Okay, that was a long time ago, and I'm still worried about my mistake, but you can't say that. The tension is not equal to the weight because it's accelerating down. But I can get an expression for the tension right here. I'll do that. T equals, I'm going to add M1G to both sides. I get M1G minus M1A. And that's my tension due to block 1. Now we can go over and draw the forces for block 2. It's a little bit more complicated. So I have, first of all, I need to pick my coordinate system. And since the block is going to be accelerating this way, I'm going to pick this as my x-axis and this is my y-axis. It doesn't have to be the same as over here because we've already translated these magnitudes over. By picking this axis as for my situation, I'm going to have the acceleration in just the x direction and not the y direction. And that's going to make things easier. So let me just draw that axis right here. Now you do want to have your x and y axis perpendicular to each other. Otherwise, you're setting yourself up for a world of hurt. Trust me on that one. Okay, so the first thing I have is the gravitational force, M2G. Now remember, the gravitational force is down. It's not perpendicular to the plane. Okay, so just because I put my y-axis this way doesn't mean that my gravitation is that way. The next I have is the normal force, which normal means perpendicular. It's perpendicular to the plane, so it had to be this way. Next I have my tension. And then finally I have my friction. Friction is parallel to the plane, opposing the motion. So if the block's sliding up this way, then my frictional force is going to be that way. Now, I do know one angle, and I've done this before, but this angle right here is theta. If this angle's theta, that angle's theta. And I've derived that before. I don't want to derive it right now because I just don't want to. So with that, I have these two components of the gravitational force. I have the y component and the x component. So let's look at the y direction first, because I know the net forces in the y direction are 0. So I can say F net y, because it doesn't accelerate this way. That was my choice. F net y is going to be equal to n. And then I have a component of the gravitational force pulling down. Since this is the adjacent side, that's going to be m2g times the cosine of theta. So it's going to be minus m2g cosine theta. And that's it. And in fact, I'm going to need to get the value for the normal force because I need that for the friction. So I'm going to say n equals m2g cosine theta. I just added that to both sides. So that's that. Now let's look at the x direction. So in the x direction, I have actually 3 forces. I have the tension, T in the positive x direction, and then I have 2 in the negative x direction. I have this component of the gravitational force. Since this is the hypotenuse and that's the opposite side, this is going to be equal to minus m2g sine theta. And it's minus because it's in the negative x direction. And then I have this frictional force. I can put minus frictional force equals m2a, because this is accelerating up the plane, so a is in the positive x direction. Now I can calculate the frictional force. F friction is going to be mu k times the normal force, which is m2g cosine theta. And I can put that in down here. I can also put in this value for my tension. So I'm going to put in tension. And I'm going to put in frictional force. And I'm going to move to another sheet of paper. I told you this one's longer. Okay, so I'll scoot this down so we can see what we're doing here. So the first thing I can do is put in the tension right here. So I'm going to say tension is going to be equal to m1g minus m1a. And then I have this term right here, minus m2g sine theta. And then I have this term, which is this right here, minus mu k m2g cosine theta, and then I have equals m2a. Okay, so now I can put this. Okay. Now I want to solve for a, right? So here I have an a term, and here I have an a term. So I'm going to add m1a to both sides, and I get m1g. Now, when you have a lot of terms like this, don't try to make shortcuts. Even I don't want to make shortcuts because I'll make a mistake. Minus m2g sine theta minus mu k m2g cosine theta equals a times m1 plus m2. Now I can divide both sides by m1 plus m2, and I get my answer. So is there anything to simplify here? So let's see, I have g in every term. I have some stuff. I don't know. I'm just going to leave it like that. So I'm going to say a equals m1g minus m2g sine theta minus mu k m2g cosine theta, all of that over m1 plus m2. Okay, that's my answer. Now let's check, right? It's check time. So the first thing I want to check is, does this have units for acceleration? So I know g is in newtons per kilogram, which is the same as an acceleration. So these are good. And then, but I have multiple, and then on the bottom I have mass, right? Add 2 mass together, it's kilograms. So that cancels right there, it cancels right there. Sine theta has no units. Coefficient of friction has no units. Mass, so it does. It has the correct units. The next thing I want to check is what would happen if I let my friction coefficient go to 0. What if mu k goes to 0? Then this whole term goes away. And if that term goes away, then I should get this, right? This is my acceleration with no friction, and you see I do get the same thing. So that's good. So I'm pretty happy right there. I'm going to go ahead and put in my values and get a value for the acceleration of, with M1 is 100, M2 is 50, and theta is, I picked 30, and mu k is 0.1. So let's put out the calculator here. Let's see, scoot this over. Okay, so I'm just going to put my values in. M1 is 0.1, enter, 9.8 times. And now I'm going to do M2 is 0.05, enter. G is 9.8 times. And then theta was 30 degrees, so 30 sine times. And then I'm going to subtract that, right? I'd have that number, and I subtract the two, and I get, now I have that. Now I have mu k is 0.1, enter, 0.05 times 9.8 times 30 cosine times, and that's also going to be subtracted. And then I'm going to divide by m1 plus m2, which is 0.15. And I get 4.617 meters per second squared. Okay, now you can see here that we could possibly have a problem. What if this stuff was greater than that and I'd have a negative number? But if I had a negative number, then I would have to change something. Because now if this block is accelerating down this way, then this frictional force would actually be in that direction. Okay, so should I solve, I guess I should, this is acceleration up. If the acceleration is down, this term is going to flip directions, right? So A down is going to be equal to the same thing. Everything's the same, m1g minus m2g sine theta plus mu k m2g cosine theta, all of that over m1 plus m2. So that's if the mass is accelerating down the plane, then I have to change the direction of that frictional force. Okay, it actually doesn't even have to be accelerating down the plane. It could be moving down the plane. If I took this block and I pushed it this way, and it actually accelerated that way, then it would, the friction force would still change, because the frictional force doesn't depend on the acceleration, it depends on the motion. So if this is moving that way, then my friction force changes direction. Okay, and that's that.